Since we can add up enthalpy changes for related reactions to get the enthalpy change of a net or composite process, it would be helpful to define a standard set of processes that, for example, formed compounds from their elements, such that we could use these processes in any context where that compound appeared. That's the idea behind the standard enthalpies of formation, and really it invokes Hess's law as we've seen it already, the fact that enthalpy is a state function. So the standard enthalpy change of reaction is defined as you see here, and we've seen that already. And what we can do is define a standard process for each of these reactants or products, A through D, each of the compounds involved. We could make use of this standard process to find the standard enthalpy change of reaction simply by adding and subtracting the standard processes. A standard process was agreed upon as the theory of thermodynamics came into focus, and it's the formation of a compound from its elements under the standard conditions, 1 bar, and for our purposes, 25.00 degrees Celsius, 298.15 Kelvin. For example, for water, the formation reaction is 1 mole of H2 gas plus half a mole of O2 forms 1 mole of H2O. Some important things to note about this reaction is that 1 mole of product is forming. We do this by convention, and we use fractional coefficients in the reactants to achieve this if need be. And note the phases. The phases used are the phases of those substances under these standard conditions, 1 bar and 25 degrees Celsius. So under those conditions, hydrogen is a gas, oxygen is a gas, and water is a liquid, and that's where these phases come from. The enthalpy change for this process is known as the standard enthalpy change of formation. And so it's got the little circle to denote standard conditions, it's got the sub m to denote per mole, it's a molar quantity, and the F stands for formation, a heat or an enthalpy change of formation. The standard state, as we just mentioned, is defined as the state at 1 bar of pressure and 298.15 Kelvin or 25 degrees C unless otherwise stated. The elements themselves have heats of formation of 0. What this does is it defines the collection of all the elements as a standard situation with enthalpy 0. And so the formation of an element from itself, of course, trivially has an enthalpy change of 0. If we take H2 gas and we want to know the heat of formation of H2 gas, well, H2 gas is made from its elements simply by starting with H2 gas and ending with H2 gas. And so, of course, trivially, since we've done nothing, delta H here is equal to 0. So the elements themselves have heats of formation or enthalpies of formation of 0. Most enthalpies of formation are negative because compounds tend to be more stable than their elements. And if you look in a table, you'll see that this is the case. The nice things about enthalpy changes of formation is that chemists of old have done the hard work for us. There are tables upon tables, and if you visit the link right here, you'll see on Wikipedia a table of many, many, many enthalpies of formation that are known. And we can now use these numbers to construct any reaction we want to that involves the compounds listed, and that's really, really nice. And of course, since we can sum the formation reactions to create any reaction that we want to, we can sum the corresponding enthalpy changes to see the change in reaction enthalpy for any of the reactions we might want to study involving these compounds whose heats of formation have been determined. So let's see how this works. How do we construct a reaction enthalpy from enthalpies of formation? Well, it's a step-by-step process that works like this. The first step is to obliterate the reactants, as I like to call it, back to their elements, and that's going to require an investment of enthalpy typically, right? So delta H's of formation are typically negative. We're going to have to input enthalpy, input energy, input heat in order to convert a compound back to its elements, which is the reverse of formation. The enthalpy change associated that, notice, is the negative of the sum of all the enthalpies of formation here, because what we're doing is the reverse of formation, taking a compound back to its elements. I should mention here, and I'll probably mention this again, but it's important to keep in mind that when you do this sum over all the heats of formation, it is very important to respect stoichiometry. If you have, for example, 2 molecules of H2O involved as reactants in a reaction, you need to multiply the heat of formation for water by 2 when calculating this sum, delta H1. You'll sometimes see this formula written, in fact, with a little new symbol in front of the delta H of formation, just to emphasize that you need to multiply by the stoichiometric coefficient. This is kind of a universal symbol for stoichiometric coefficient, the letter nu, while you're calculating this change in enthalpy. So with that out of the way, we've converted the reactants to their elements. What do we do next? Simply kind of the opposite process, but building the products from the elements now instead of the reactants. And because of the magic of conservation of mass, the elements that you generate from the reactants will be just enough atoms and just the right types of atoms to construct the products, right? And this is going to involve a release in enthalpies, since what we're doing is formation in the forward direction now, and those enthalpies are typically negative. The formula here looks very similar with two important differences. Now we're summing over the products, and you do still need to respect stoichiometry, and there's no negative sign here now. Now we're looking at just the enthalpies of formation themselves, since we're doing formation in the forward direction. Step 3 is simply to add delta H1 and delta H2 together, which, because we have on the whole converted reactants to products, the sum of these two enthalpy changes is going to be equal to the enthalpy change of reaction. Just as an aside, you'll often see this formula written out with the sums explicitly here for delta H1 and delta H2, and I would say on a crib sheet, for example, I would write out the whole formula instead of writing out all 3 lines, but I just wanted to do it this way so that you can see how to apply the process. So let's look at an example. The decomposition of silver nitrate, AgNO3, to form AgNO2 plus 0.5O2. So step 1 is to obliterate the reactants to their elements, which is going to involve an investment of enthalpy. And we will have to look up the heat of formation of solid silver nitrate. That turns out to be negative 124.4 kilojoules per mole. We have 1 mole of AgNO3 reacting. Notice that I'm respecting the stoichiometry here and being careful and multiplying by 1. That gives us delta H1 for reverse of formation, producing the elements from the compound, as positive 124.4 kilojoules. Next step, construct the products from these elements. And let's just survey the elements really quickly to make sure that there's mass balance here. So breaking down AgNO3, we get 1 mole of Ag from the 1 mole of silver built into this compound. We have 1 mole of Ag in the products, so that's balanced. We get half a mole of N2, because 1 nitrogen atom comes from AgNO3, and N2, the elemental form, has 2 nitrogen atoms. And indeed, we have half a mole of N2, or 1 nitrogen atom, in the products. And we get 1.5 moles of O2, because we have 3 oxygen atoms in the reactants. And indeed, we have 3 oxygen atoms in the products as well. Half a mole of O2, that's 1 mole of O, plus 2 moles of O built into AgNO2. So there's mass balance here, as there always will be. When we construct the products from these elements, we have to add up the heats of formation of AgNO2 and O2. The heat of formation of silver nitrite, AgNO2, turns out to be negative 44.4 kilojoules per mole. Again, I'm respecting stoichiometry, multiplying by 1 mole because the coefficient here is 1, right? And what's the heat of formation of O2? Well, it's the elemental form of oxygen, and so its heat of formation is simply 0 kilojoules per mole. I'm being very systematic and very careful here, though, and still multiplying by the stoichiometric coefficient on O2. Even though I know I'm going to get 0, I still want to respect the stoichiometry and just be careful. So, delta H2 for step 2, the process of producing the compounds from their elements, negative 44.4 kilojoules. To determine the overall enthalpy change of reaction, simply add the two. We have positive 124.4 minus 44.4 kilojoules. We'll divide by 1 mole, since we're looking at 1 mole of reaction events here, and what we get is positive 80 kilojoules per mole for the enthalpy change of reaction for this process. So that's pretty nice. We've blown it up and kind of slowed it down and done it systematically, but ultimately what we can do is use the enthalpies of formation of the reactants and products to calculate very simply, using a very straightforward sum, the enthalpy change during a reaction. So in summary, Hess's law really captures the idea that enthalpy is a state function. Hess's law says that if a set of reactions, let's call them R1 to Rn, a set of processes that convert some reactants to some products, add up to a different reaction, Rn plus 1, then the enthalpy change of that R sub n plus 1 reaction is equal to the sum of the enthalpy changes of all the R1 to Rn. Using the enthalpies of formation in particular is just an application of this idea where the set of reactions happen to be the formation reactions of the reactants and products. And here's that formula for you again one more time. The enthalpy change of reaction is equal to the sum of the enthalpies of formation for all the products respecting stoichiometry minus the sum over all of the reactants of the enthalpies of formation of the reactants, again respecting stoichiometry.